Now, we've said that light is a wave, but for a long time, people didn't know that. People didn't realize that. In fact, there was a big debate that we'll talk about later because it doesn't look like a wave. And one of the reasons it doesn't look like a wave is because of what we just talked about, that it goes so fast, you can't see it. The other reason is because a wave of light is so small. Light wavelengths are measured in nanometers. Like a nanometer, the prefix n stands for nano. That's a metric prefix. Nano is 10 to the negative ninth, or 1/1 billionth. A nanometer is 1/1 billionth of a meter. That's super duper small, and that's what we have to use to measure light wavelengths in units that we can manage without using a lot of scientific notation. But you need to know that in order to use this equation, V equals F lambda, that's the wave equation. It still applies to light because light is a wave. Wavelengths have to be in meters. All right, so here's the deal. We measure wavelengths in nanometers with light, but we have to convert it to meters in order to put it into this equation. So we got to know how to do that. You got to know how to do that. So I'm going to teach you how to convert from nanometers to meters. It's super, super easy. So here's an example. Violet light has a wavelength of 400 nanometers. How many meters is this? All I got to do is convert it to meters. So 400 nanometers. Ready? Here's all you do. All you got to do is remember that nano in means times 10 to the negative 9. So all we got to do is drop that in, and then we're going to substitute times 10 to the negative 9. I mean, literally, it's that easy. Everywhere you see an n, as long as you remember that n is times 10 to the negative 9, drop the n, substitute it for times 10 to the negative 9th, and you are done. 400 nanometers equals 400 times 10 to the negative 9th meters. Now, some people right now are going, well, don't we need to put the decimal in here and change the exponent? You could do that if you want to, but I don't care. Your calculator will take this number right here. And I'll show you how to do that in just a second after we use this problem. We'll do it in this problem. So the converting is so that we can use V equals F lambda. That's the key. So when it says, what's the frequency of violet light? Well, the first thing we have to remember is that we already know the speed of light. That's another one of those givens, kind of like the speed of sound you knew was 340, and that wasn't given to you. Well, now we know that the speed of light is 3 times 10 to the 8th, and we just were given its wavelength. So the first thing we would have to do with this problem is convert the wavelength to meters, which we did here. We know the speed is 3 times 10 to the 8th. We're looking for the frequency, and again, there's our wavelength, 400 times 10 to the 9th, which is what we converted. So what we're going to do is divide by 400 times 10 to the 9th on both sides. So 3 times 10 to the 8th divided by 400 times 10 to the negative 9th. Here we go. I'm going to use parentheses first. 3 times 10, and then I need an exponent on there, and that's this a to the b button. 3 times 10 to the 8th. And then I'm going to put my cursor back out here and complete that parentheses. I need the parentheses there because I need this calculator to know that is one number. And it is one number. It's a number that's expressed in scientific notation. 3 times 10 to the 8th divided by 400 times 10 to the 9th. Once again, parentheses, 400 times 10, and then I'm going to a to the b button to get an exponent up here, and then times 10 to the minus 9. Put my cursor out here, and also you can use this button here. Close the parentheses, hit enter, and we get 7.5 times 10 to the 14th hertz. That's our frequency there. Strongly recommend that you learn how to use this calculator. That's going to be what's going to be available to you on the homework and on the tests and quizzes. So this is working with wavelengths, very, very small. We got to know how to convert nanometers to meters. Now, as far as wavelength is concerned, there are lots of light wavelengths that you may or may not have known about before. So first thing I need to tell you, this in yellow up here at the top says this is all light, but not all is visible. So that's something that a lot of people don't understand. Well, light is the stuff I can see, right? Well, yes, it is, but you have to understand, again, it's real easy for us to look at this in a very human-centric way and think that light is just the stuff that we can see. Well, you need to realize that your eyes are specifically attuned to a very small portion of what is actually light. and more correctly, it's termed electromagnetic radiation. All of this stuff is light. Gamma rays are light. X-rays are light or electromagnetic waves. UV stands for ultraviolet light. And then right here, I want you to notice this teeny tiny little sliver in the middle that you have to blow up to even see the colors. Guys and gals, that's visible light. That's the only part of this entire spectrum that we can see. Now, that's just us. There are actually other animals that can see or sense other portions of this spectrum, but we can't. So we got to understand, just because we can't see it doesn't mean it's not light. All of this stuff is the same. It's all a wave. It's on an electromagnetic wave. The only difference among the regions of this spectrum is the frequency and wavelength. And our eyes are specifically not tuned to those, but it's the same stuff. It's just a different frequency. Infrared radiation is infrared light. And radio waves, all of this stuff, you need to know all of these regions of the electromagnetic spectrum, right? And I'll give you a way to learn that in just a minute. But you need to know that, first of all, a couple of things. Notice the words up here: increasing frequency and increasing energy. Energy and frequency are directly related to each other. And hopefully you learned that with that lab activity that you did. The higher energy light that we saw that made a longer, a brighter glow on that plastic, those were the higher frequency lights, colors, the blues, the purples, which is on this end, but we're talking about the entire spectrum, not only visible. When you look at the things on this spectrum, you might notice that you probably have a negative reaction to these things. Gamma rays, you might think about the Hulk. X-rays, when you go get an X-ray, the doctor goes to the other room, right? He doesn't even stay in there. UV, we got to protect against that with sunblock. All of this stuff is kind of nasty. We got to protect against it. The reason the doctor has to go to the other room is because X-rays are dangerous. And you might be going, well, if they're dangerous, why are they doing it to me? Well, you need to know that it does create DNA damage. But when you have one X-ray, it's a small enough amount of damage that your cells can correct it. But with the number of X-rays that a doctor is giving every day or a radiologist is giving every day, that can result in enough damage that it overwhelms the cell's capability to repair, and it can result in cancer. So they've got to protect themselves. But here's the point. Everything on this left end is the highest energy regions of this spectrum that we can get. Again, on this side, we have increasing, as we go to the left, the energy and the frequency increases. Higher frequency, higher energy. But notice wavelength is the opposite direction, because wavelength is inversely related to frequency, and we've already talked about that with sound. The higher the frequency, the lower the wavelength, and vice versa. And you can see that depicted here as we get to this way, as we look at this wave. On this end, we have big wavelengths but low frequencies. The radio wave is the lowest frequency and also the lowest energy. Radio waves are not dangerous. Neither are infrared waves. Infrared radiation is really just heat. It's not dangerous because it doesn't have enough energy. We start to get dangerous up in this end. These have enough energy to actually pierce your skin and do damage underneath. So this is the entire electromagnetic spectrum. In addition to this, the entire electromagnetic spectrum, you also need to know the visible spectrum. That's just visible light, right? So again, here's the entire electromagnetic spectrum. It's actually flipped the other way now. Gamma rays was on the left, now it's on the right. And we go all the way down to radio waves down at the bottom. Microwaves are in here too. So a way to know the entire electromagnetic spectrum is this little phrase right here: red Martians invaded Venus using X-ray guns. So this will help you to remember all of these specific regions. R for radio, M goes for microwaves, the I is infrared, V in Venus. People are going, well, what is that? Well, that's visible light, which is this tiny little sliver right here. And we blew it up to see all of the colors. The only reason we define this region of the spectrum, or really any of these regions, is how we use them or how they affect us. That's the only reason why we define these regions. Otherwise, there's no real demarcation between them, including visible light. The only reason we define that region of visible light, which is, by the way, you need to know this, from 400 to 700 nanometers, it's because we can see it. U stands for ultraviolet. Ultra means above, so this is above the violet light, frequencies above violet. Infra means below, so these are frequencies below red light. X-ray, X-rays. And the G stands for gamma rays. And what you need to know about this little saying, red Martians invaded Venus using X-ray guns, is that it puts all of the regions in order of, and this is important, puts all the regions in order of increasing frequency and increasing energy. So you need to know, again, that the radio and microwave end of the spectrum, that's low energy, low frequency, safe stuff. But the X-ray, gamma ray end of the spectrum, high energy, high frequency, and that is nasty stuff. Now, the other thing you need to know about the spectrum is you need to know the order of the visible spectrum as well. This looks like a rainbow, and you might not have ever noticed this, but rainbows always turn out in this order. And you need to write this down. There's a guy whose name is Roy G. Biv. Actually, that's not his name. But we use those letters to represent the colors of the spectrum. Roy, R-O-Y, G, Biv, B-I-V. R stands for red, O stands for orange, Y stands for yellow. Notice we're going in order of increasing energy and frequency. And this is just with the visible spectrum, okay? Red Martians invaded Venus using X-ray guns. That's the whole spectrum. But you need to also know the colors of the visible spectrum in order of increasing frequency and wavelength. Red, orange, yellow, green, Roy G, and then Biv, blue, indigo, violet. Now you need to know indigo is kind of the same thing as blue. And the only reason we have it in there is so that we don't sound silly saying Roy G. Biv. It's really the blue violet end. I'm going to refer to this as the blue violet end. I'm going to refer to this end as the red orange end. It's really red, orange, yellow, green, blue, violet. Okay. But we put the I in there just so it makes a Biv, so it makes a word so that we can remember Roy G. Biv. It's a good way to remember the colors of the visible spectrum in order of increasing frequency. Red, orange being the low frequency, low energy end. The blue, violet being the high frequency and high energy end.